Good morning, my dear students. Um, Today topic is Unit 4, Cayley-Hamilton theorem with examples. In this unit, touches are objectives, interactions, characteristic equation, and polynomials. Working rule to find the characteristic equation, inverse matrix. Let us sum up. And some keywords, some terminal questions. The first one is subjectives. The characteristic polynomial provides a good example and invariant for certain types of objectives and topics like graph sets and all have associated matrix. The characteristic polynomial of which is of combinations importance and Cayley-Hamilton theorem always provides the relationship between the powers of A. Okay, so which allows one to simplify expressions involving such a powers and evaluate them without having to find the powers A power of n or any higher power of A, higher power of A. Introductions. So Cayley-Hamilton theorem was given in the years 1858 by two mathematicians, Arthur Cayley and Williams Rowan Millers. So that is Hamilton theorems that all real and complex square matrices will satisfy their own characteristic polynomial equations. This implies that when a square matrix is transformed into a polynomial, then this polynomial will be equal to 0. This polynomial will be equal to 0. So Cayley-Hamilton theorem is a very important result that is used in advanced linear algebra to simplify linear transformation. In this articles, we will learn more about the Cayley-Hamilton theorem, its statements, proofs, associated examples. The Cayley-Hamilton theorem is usually presented in standard and undergraduate courses in linear algebra as an important result. Recall that it says that any square matrix is a root of its own characteristic equation. That is, a square matrix satisfies its own characteristic equations. The next one is characteristic equation and characteristic polynomial. Cayley-Hamilton theorem is one of the most powerful results in linear algebra. This theorem basically gives the relations between a square matrix and its characteristic polynomial. One important application of this theorem is to find the inverse and the higher powers of matrix. And the sum of the n eigenvalues of A is here same as a trace of A. The product of n eigenvalues of A is same as a determinant of A. If lambda is an eigenvalues of A, then the dimension of E into lambda, so E means eigenvalues, is at most of the multiplicity of A. Characteristic equations. The modulus A minus lambda I equal to 0 is called the characteristic equation of the matrix capital A. Now, sorry, modulus A minus lambda I equal to 0, we get n roots for lambda, and these roots are called eigen roots, eigenvalues, characteristic values. Corresponding to each values of lambda, the equation Ax equal to lambda x as a non-zero solution vectors capital X. So if capital X are be the non-zero vectors satisfying Ax equal to lambda x, when lambda equal to lambda r, capital X r is said to be a eigenvectors of the matrix capital A corresponding to lambda r. characteristic equations or characteristic polynomial. So the determinant a minus lambda I when expanded will give a polynomial which we call as characteristic polynomial of A. Characteristic polynomial of matrix A. So the next one is working rule to find the characteristic equations for a 3 cross 3 matrix. Already we know that 3 cross 3 matrix formula, that is characteristic equation formula, is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. S1 is the sum of the main diagonal elements. S2 equal to sum of the minor of main diagonal elements. S3 equal to determinant of A. This is for 3 cross 3 matrix. The next one is 2 cross 2 matrix characteristic equations formula. That formula is lambda square minus s1 lambda plus s2 equal to 0. S1 equal to sum of the main diagonal elements. S2 equal to determinant of A. Determinant of A. So in the next one, examples. Okay, so find the characteristic equation of the matrix capital A equal to 1, 2, 0, 2. 1, 2, 0, 2. Okay, so first you find out that what are the characteristic equations. Okay, so now you take capital A equal to this matrix 1, 2, 0, 2. Now we want characteristic equations values. So that is S1 and S2. Our formula is lambda square minus S1 lambda minus S2 equal to 0. S1 lambda plus S2 equal to 0. S1 is a main diagonal elements. Our main diagonal values is 1, 2. Okay, so that is we get 3. So S2 equal to determinant of A equal to, we find out our values is 2. Okay, now you substitute this formula. Lambda square minus S1 lambda plus S2 equal to 0. So our S1 values is 3 and S2 values is 2. Substitute that formula. We get our equation is lambda square minus 3 lambda plus 2 equal to 0. So next one is find the characteristic equation of the matrix. Capital A equal to 3, 1, minus 1, 2. So now we take our, we want the characteristic equations. Now you write down the formula. This matrix is 2 cross 2 matrix. So that is our formula is lambda square minus x1 lambda plus x2 equal to 0. So s1 equal to, you take the main sum of the main diagonal elements. S2 equal to sum of the minor of the main diagonal elements. Okay. So now you get the result as S1 equal to 5 and S2 equal to 7. Now you substitute, therefore the characteristic polynomial is lambda square minus 5 lambda plus 7 equal to 0. Next one is Cayley-Hamilton theorem. So statement every square matrix satisfies its own characteristic equation. Uses of Cayley-Hamilton theorem. Uses of Cayley-Hamilton theorem. To calculate the positive integers power of A. To calculate the inverse of a square matrix capital A. Okay. The next one is operation on matrix using Cayley-Hamilton theorem. Show that the now you see our problems examples. So show the matrix 1 minus 2 2 1 satisfies its own characteristic equations. Solutions. Its characteristic equation can be written as lambda cube minus s1 lambda square. Uh, sorry, that this is our 2 cross 2 matrix. So here we are using the characteristic equation can be written as lambda square minus s1 lambda plus s2 equal to 0, where s1 is the sum of the main diagonal elements, s2 equal to determinant of A. Okay, so now our elements is that main diagonal elements is 1 1. So s1 equal to 1 plus 1 we get result is 2 and s2 equal to the determinant of A. You already we know that 2 cross 2 matrix determinant. Now you will get the result is 5. Now substitute terms. Therefore, the characteristic polynomial is lambda square minus 2 lambda plus 5 equal to 0. That is to prove a square minus 2a plus 5i equal to 0. So a square equal to a into a. Now already we know that a matrix take few times of the same matrix, multiply each row and each column. So we get the result is minus 3, minus 4, 4, minus 3. This is our A square matrix value. And we know that A square minus 2A plus 5I equal to, now you substitute A square matrix and A matrix and I. I is the identity matrix. So now simplify this, we get our result is 0. We get our result is 0. Therefore, the given matrix satisfies its own characteristic equations. Own characteristic equations. The second one problem is if capital A equal to 1 minus 2, 2, 1. So return write A square in terms of A and I using Cayley-Hamilton theorem. Cayley-Hamilton theorem. So Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equations. The characteristic equation of capital A is A square minus S1 lambda plus S2 equal to 0, where S1 equal to sum of the main diagonal elements. Okay, and S equal to determinant of A. So, and S1 equal to, we get the result is 6 and S2 equal to 5. Now, you substitute characteristic equations formula, we get our equation is lambda square minus 6 lambda plus 5 equal to 0. Okay, by Cayley-Hamilton theorem, Cayley-Hamilton theorem, lambda equal to A and A square minus 6A plus 5I equal to 0. This is our Cayley-Hamilton theorem equations. Now you find out A square, you will get the one of the matrix. Then substitute and simplify this. We get our characters satisfy its own characteristic equations. The given matrix satisfy. So first you find out A square. What is our A square value? A square terms is 6A minus 5I. So I is the identity matrix. This is our 2 cross 2 matrix. No? 1, 0, 0, 1. Okay. So what is our matrix? Our A matrix. Our A matrix is 1 minus 2, 2, 1. Okay, now you simplify, we get A square. Then again you simplify, substitute A square and A and I. Okay, so already we know that I is the identity matrix 1, 0, 0, 1. They give us matrix here, A square equal to, we get some next one is inverse matrix using Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem. Find A equal to 2 minus 1, 2, minus 1, 2, minus 1, 1, minus 1, minus 1, 2. Okay, so this characteristic equation is, this is our 3 cross 3 matrix. So A equal to, you will take first A equal to 2 minus 1, 2, minus 1, minus 2, minus 1. 1 minus 1, 2. Okay, its characteristic equation can be written as lambda cube minus S1 lambda square minus S2 lambda plus S3 equal to minus S3 equal to 0. So where S1 equal to sum of the main diagonal elements. Okay, and S2 equal to sum of the minor of main diagonal elements. And S3 equal to determinant of A. We get our result is S1 equal to 6 and S2 equal to 8 and S3 equal to 3. Now you substitute that lambda cube minus S1 lambda plus S2 lambda lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. S3 equal to 0. So we get the characteristic equation as lambda cube minus 6 lambda square plus 8 lambda minus 3 equal to 0. Okay, then you frame that Cayley-Hamilton theorems. What is that? The given matrix, every square matrix satisfies its own characteristic equations. Okay, so that is what is our characteristic equations, lambda cube. Then you write down a cube. And the next one is 6 lambda square. Next term is minus 6a square. The next one is 8 lambda. That is plus 8a. Okay. The last one is minus 3. So that is your Cayley-Hamilton. We are using Cayley-Hamilton theorems. So minus 3i. Minus 3i. First you find out a cube. First you find out a cube. So before that you find out a square. So a square is a into a. We get our matrix is minus 7, minus 6, 9, minus 5, 6, minus 6, 5, minus 5, 7. Then you find out a cube. So that is we bring that a square into a. Okay, so already we know that a square matrix. What is that matrix? 7, minus 6, 9, minus 5, 6, minus 6, 5, minus 5, 7. And A matrix is 2, minus 1, 2, minus 1, 2, minus 1, 1, minus 1, 2 here. Then you multiply, we get our matrices 29, minus 6, 38, 22, 23, 28, 22, minus 22, 29. 29. Now, already we know that already we know that Cayley-Hamilton theorem equations a cube minus 6a square plus 8a minus 3i. Then you substitute a cube and a square, a identity matrix. Okay. Then you simplify, we get the final answer is 0, 0, 0, 0. Every element is 0. Okay. So that is therefore the given the matrix satisfies its own characteristic equations. Next one you find out a power 4, a power 4. So that is now you take equation number 1. Equation number 1 is a cube minus 6a square plus 8a minus 3i equal to 0 implies a power of cube. A power of cube, the remaining term will take right hand side 6a square minus 8a plus 3i. Okay, this is our equation number 2. Multiply by a on both sides. A power of 4 multiply by a on both sides. A power of 4 equal to 6a square a cubed minus 8a square plus 3a equal to 6 of all the terms. 6 of all the terms. That is a cube. A cube. Already we know that a cube terms. A cube terms. So 6a square minus 8a plus 3a. That term will substitute in this one. So 6 into 6 of 6a square minus 8a plus 3i minus 8 minus 8a square plus 3a. Now you simplify these equations. We get 28a square minus 45a plus 18i. 18i. Now you substitute a square matrix and a matrix and identity matrix. Identity matrix. Then you simplify, we get our terms, we get our matrices, the final matrices 124 minus 123, 162, minus 95, 96, minus 123, 95, 90, minus 95, 124, 24. The next one is find A inverse. A inverse. Next one is find A inverse. So multiply one, multiply by one, a power of minus one, a power of minus one. We get our equation as a square minus 6a plus 8i minus 3a power of minus 1 equal to 0. Now you take 3a power of minus 1, the remaining terms goes right hand side. So a square minus 6a plus 8i. So the right hand side term is this. Okay. Now already we know that a square value and a and I. Okay. So 3a power of minus 1 equal to 7 minus 6 9 minus 5 6 minus 6 5 minus 5 7. So minus 6 of A matrix. What is our A matrix? 2, -1, 2, -1, 2, -1. And the third row is 1, -1, 2. Okay, so plus 8 of identity matrix. What is our identity matrix? This matrix is 3 cross 3 matrix. Our problem is 3 cross 3 matrix. So we take identity matrices here 3 cross 3 matrix. That is 1 0 0 0 1 0 0 0 1 0 0 1. Now you multiply -6 plus 8. Okay, so 7 minus 6, 9, minus 5, 6, minus 6, 5, minus 5, 7, minus of -12, 6, minus 12, 6, minus 12, 6, minus 6, 6, minus 12. So plus 8, 0, 0, 0, 8, 0, 0, 0, 8. We get our final matrix is 3, 0, minus 3, 1, 2, 0, minus 1, 1, 3. Okay, so the final one is a power of -1 equal to 1 by 3. The right hand side value of this matrix 3, 0, minus 3, 1, 2, 0. The third row is -1, 1, 3. Okay, the left hand side is 3 a power of -1. Just you need to take 1 by 3 on the right hand side. Okay. Our final answer is a power of -1 equal to 1 by 3 of 3 0 minus 3 1 2 0 minus 1 1 3. The next one problem is the next one example is if a equal to the first row is 2 1 1 0 1. Now the second row is 0 1 0. The third row is 1 1 2. Okay, verify Cayley Hamilton theorem the first one. Second one, find a power of 4 and a power of -1. Third one is a power of 8 minus 5 a power of 7 plus 7 a power of 6 minus 3 a power of 5 plus a power of 4 minus 5 a power of 3 plus 8 a square minus 2a plus I. You find out the base of this. First, you take the matrix. So this is our 3 cross 3 matrix. Already we know that we want the characteristic equations. What is that formula? Lambda cube minus S1 lambda plus S2 lambda. Lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. S1 is the sum of the main diagonal elements and S2 equal to sum of the main diagonal elements. S3 equal to product of A. That is, sorry, determinant of A. Okay. So now our main diagonal elements is 2, 1, 2. No? So when you added all these elements, we get our result is 5. Okay. Next one is S2. S2 you simplify. Um, you simplify 1 0 1 2 and 2 1 1 2 2 1 0 1. Okay, these three 2 cross 2 matrix, we get our result is 7. We get our result is 7. And S3 is the determinant of A. S3 is the determinant of A. We get our result is plus 3. We get our result is plus 3. Now, you take our characteristic equations and then substitute each value. Say S1, S2, S3. Okay. And S1 values is 5 and S2 values is 7, S3 values is 3. Okay, so that is lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0. And the next one is Cayley-Hamilton theorems. Cayley-Hamilton theorem. You find the Cayley-Hamilton theorem. So that is a cube minus 5a square plus 7a minus 3 equal to 0. Okay. So lambda equal to a. So substitute in our characteristic equations. Characteristic equation. First you find out a square, then a cube. Okay, identity matrix already we know that 1 1 0 0 0 1 0 0 0 1. Okay, so first you find out a square. A square means what? A into A. We get our result as 5 4 4 0, 1, 0, 4, 4, 5. Okay. Then a cube. Then we find out a cube. A cube means a square into a square into a. So a square matrix into a matrix. Okay. So the final answer is 14, 13, 13, 0, 1, 0, 13, 13, 14. Okay. Now you take the characteristic equations. So a cube minus 5a square plus 7a minus 3i. Okay, you substitute each matrix values, we get our final result is 0, 0, 0, 0. So therefore, the given matrix is satisfy Ohm characteristic equations. Ohm characteristic equations. Therefore, the given matrix satisfies its own characters equation. Next, you find out a power 4. A power 4. So, already we know that the Cayley Hamilton equations. That equation is a cube minus 5a square plus 7a minus 3i equal to 0. Multiply by a now. Okay, so a of a cube minus 5a square plus 7a minus 3i equal to a into 0. A into 0. That is a power 4 minus 5a square a cube plus 7a square minus 3a equal to 0. So a power 4 equal to that is a power 4 equal to 5 a cube minus 7a square plus 3a. Now you substitute a cube matrix and a square matrix and a matrix. We get our final result is now you put it in this equation. We get our final result is 41, 40, 40, 0, 1, 0, 0, 0, 41, 0, 0, 41. The next one is to find A inverse. To find A inverse. Already we know that A cube minus 5A square plus 7A minus 3I equal to 0. Multiply by A power of minus 1. A power of minus 1. Okay, so multiply on both sides A power of minus 1. So A cube minus A power of minus 1 of A cube minus 5A square plus 7A minus 3 equal to a power of minus 1 of 0. So a power of minus 1 a cube minus 5 a power of minus 1 a square plus 7 into a power of minus 1 a minus 3 a power of minus 1 equal to 0. Now you simplify these equations. A square minus 5a plus 7i minus 3a power of minus 1 equal to 0. Okay, so then a square minus 5a plus 7i equal to 3a power of minus 1. Then a power of minus 1 equal to 1 by 3 a square minus 5a plus 7i. Already we know that a square matrix and a matrix and identity matrix. You substitute in this equation, we simplify, we get the final result is 1 by 3, 2 minus 1 minus 1, 0, 3, 0, minus 1 minus 1, 2. Okay, the next one, the final one, this is the final one. To find a power of 8, a power of 8 minus 5 a power of 7 plus 7 a power of 6 minus 3 a power of 5 plus a power of 4 minus 5 a power of 3 plus 8 a square minus 2a plus I. Okay, so we know that Cayley Hamilton equations. So Cayley Hamilton equation is a cube minus 5a square plus 7a minus 3. So now you divide this, we get our final answer is a power 5 plus a. The remainder is a square plus capital A plus I. Capital A plus I. Okay, so this equations we written as a power 8 minus 5a square a power 7 plus 7 a power 6 minus 3 a power 5 plus a power 4 minus 5 a power 3 plus 8 a square minus 2a plus I. Okay, so equal to the Cayley Hamilton equations into quotient plus our remainders. Remaining equations. Okay, so our Hamilton equations is 0. No? So you substitute in this place, we get 0 plus a square plus a plus I. Already we know that a square matrix and a matrix and identity matrix. You substitute in this equation, you simplify this matrix and we get our final result is 855,030,558. Okay. Keywords. So here polynomial of degree, Cayley-Hamilton theorem, matrices, square, rectangular, blocks, power of matrix. So the next one is some terminal questions. These are all some terminal questions. Verify Cayley-Hamilton theorem and find a power 4 and a power minus 1. Then a equal to 2 minus 1 2 minus 1 2 minus 1 1 minus 1 2. So our answer is here. So S1 equal to this. S2 8 and S3 equal to 3. Our characteristic equation is lambda cube minus 6 lambda square plus 8 lambda minus 3 equal to 0. And a square values is here 7 minus 6 9 minus 5 6 minus 6 5 minus 5 7. And a cube matrix is here and a power 4 matrix is here and a power of minus. So this is the same one. Same model, other problems. Okay, these all are some terminal questions. Okay, we'll follow this. So thank you everyone. Thank you everyone.